This presentation is a case history on backward erosion piping at Chute Levee. We'll begin the presentation with an overview of the project, followed by a discussion of the 2011 Mississippi River event that caused widespread flooding along the entire Mississippi River. Next, we'll step through a node-by-node evaluation of backward erosion piping at Chute Levee and summarize the factors that made BEP more likely and less likely during the flood event. First, a project overview of Chute Levee. The Mississippi River and Tributaries Project, or MR&T, consists of 3,500 miles of flood protection protecting more than 4 million people, 1.5 million homes, 33,000 farms, and countless vital transportation routes from Mississippi River floods. The main stem system, comprised of levees, flood walls, and various control structures, is 2,203 miles long. The focus of this presentation is on a stretch of the main stem levee at the location of Chute in Warren County, Mississippi, about 16 miles northwest of Vicksburg. A chute is a surface water flow path that typically allows flood water to transverse a low section of land. In this case, Chute is a batcher channel that connected Eagle Pass to Eagle Lake prior to construction of the main stem levee. Chute is located in the Yazoo Basin within the lower Mississippi River Valley, which is characterized by both braided and meandering alluvial deposits. Braided deposits were laid down during the Quaternary period, with the last 10,000 years corresponding to the Holocene period, marked by a low gradient meandering Mississippi River system. This meandering system is characterized by oxbow lakes as well as point bar, swale, abandoned channel, abandoned course, and back swamp deposits. This geological environment generally results in a soil profile that includes a top stratum of impervious material composed of silty and clay point bar and back swamp deposits that overlie a pervious substratum of sandy point bar and braided stream deposits. However, as alluded to in the backward erosion piping presentation, the nature of these types of deposits is variable, and this general soil profile is often more heterogeneous in nature, resulting in a geologic environment that is difficult to characterize and even more difficult to model. Details regarding the construction history of the embankment are limited. Based on a review of the Mississippi River Commission hydrographic surveys, the levee was constructed between 1915 and 1926 to the 1914 levee standard, which maintained a grade 3 feet above the 1912 Mississippi River high flood waterline and had slopes of 1 vertical to 3 horizontal on both the riverside and land side. The embankment is likely constructed of lean clay and fat clay material derived from nearby borrow sources, and since construction there have been several enlargements to the levee section, which are represented in the figure by the different color sections. The embankment as of 2011 was largely represented by the 1973 enlargement highlighted in yellow. The embankment had an average height of approximately 40 feet, a crown width of 10 feet, riverside slope of 1 vertical to 4 horizontal, and landside slope of 1 vertical to 5.5 horizontal. It's noted in USACE documents that the reach of levee that contains Chute wasn't analyzed in any way until 1973. Chute is considered one of the weakest areas along the MR&T due to poor performance during past flood events. Seepage and sand boils have been noted throughout the life of the project. One boil in particular was pointed out by a landowner in early 2010 and is suspected to have formed during the 2008 flood event. Sandbags were placed around the boil in spring of 2010, but it was noted that flow from the boils on the land side increased during the summer of that same year. Several boils were pumped in early 2011, with the pumping revealing voids at the boil surfaces up to 20 feet wide and 10 feet deep. Now, none of these voids contained pipes that continued downward or laterally from the void bottom, and the sides and the bottom of the voids appeared to be top stratum fine-grained material. Nevertheless, Chute is known to be an area where seepage and boil activity are present whenever the river rises. Now we'll take a look at the 2011 Mississippi River flood event. The first ingredients for the flood were a combination of an unseasonably wet autumn of 2010 and record snowfall in Iowa, Minnesota, and Wisconsin. Frigid cold followed, with severe winter storms piling even more snow across the upper Mississippi River states and the Ohio River Valley, with up to 40 inches of snow falling in some areas in a single month. The spring thaw began in February in the middle Mississippi and Ohio River valleys, with unseasonably warm temperatures and heavy rainfall rapidly melting the remaining Ohio Valley snowpack in less than 48 hours. This released up to an additional 4 inches of water as runoff. What followed was a series of heavy rain events from February to April. This resulted in widespread but minor flooding along the Ohio River and upper Mississippi River, with several areas of the Mississippi River Valley in flood stage beginning in late February. Between April 20th and May 7th, record rainfall resulted in portions of Missouri, Illinois, Indiana, Kentucky, Tennessee, Mississippi, and Iowa receiving 400 to 1,000% more rainfall than average. This caused the Mississippi River to rise to levels not seen since the floods of 1927 and 1937. Due to the magnitude of the flooding, upstream reservoirs were forced to hold water to delay downstream flows and reduce the peak river stage. Along the mainline levee system, sand boils ranging from the size of a baseball to large enough to swallow a large sedan had developed and were being flood fought. The MRT system was designed with 4 floodways that could divert floodwaters from the Mississippi River in order to reduce the peak river stage. 2 of these floodways, the Morganza and the Bonacary, were both activated during the flood of 1973 and were again activated in 2011. In addition to the activation of these 2 floodways, the 2011 flood also necessitated the activation of the Birds Point New Madrid floodway, which required the use of explosives to blast a breach through the Birds Point levee, resulting in the further inundation of 130,000 acres of farmland and several buildings and homes. However, when all was said and done, efforts to reduce the river stage and flood fight were successful as there were no levee failures along the Mississippi mainline MRT system. Now, let's zoom in specifically on Buckshot Levee. Following the discovery of the extensive sand boils on the landside in early 2010, the decision was made to proceed with the design and construction of a permanent repair to address the seepage-related concerns at the levee. At the time that the flood arrived, investigations had been performed and geotechnical analysis was underway. However, the design for the repair was not completed and not ready to be implemented. In order to prevent potential failure of the levee embankment, several methods of flood fighting were employed at Buckshot. The intervention actions that were taken and their effectiveness at preventing levee failure are discussed in depth in a second case history presentation for Buckshot on the subject of intervention. The remainder of the presentation will be used to evaluate potential backward erosion piping at Buckshot Levee during the 2011 flood event. This is the typical event tree for backward erosion piping that is presented in the backward erosion piping presentation. A node-by-node evaluation in the following slides will look at each node in the event tree as they pertain to Buckshot Levee in 2011. The first step in the evaluation is determining the areas along the levee that are the most susceptible to potential backward erosion piping. There are 2 locations at Buckshot Levee that were particularly susceptible to BEP based on observed poor performance during past flood events. The northern area is highlighted with a red star, and it's the location where the boils developed and were observed in 2010. This is the location where pumping of the boils revealed large voids. The second area is the southern area. Boils were observed in this location during a flood event in 1997, prompting the installation of 6 6-inch relief wells. During a 2005 flood event, additional pin boils were observed in the area, which prompted the installation of 3 additional 14-inch relief wells to reduce foundation seepage pressures. For Node 1 in the BEP event tree, a study of available information can aid in the determination of whether a continuous path of fine to medium uniform sand exists in the foundation soils beneath the levee embankment. As was stated in the backward erosion piping presentation, This node will not define a range of coefficient of uniformity because node 5, the hydraulic condition for progression, is conditional on this node. Variability in CU will be addressed in node 5. Several factors can be examined when evaluating node 1. First, a geological perspective. What was the depositional environment of the subsurface soils? Buck Chute is in the lower Mississippi River Valley, which is characterized by recent meandering stream deposits that overlie braided stream deposits. The nature of these deposits should tell us that it's likely that there's a fairly large and continuous layer of sandy material underlying the typically more impervious top stratum. By examining the geological environment, a decent characterization of the foundation soils can be made even if there are no boring logs or soil testing data available. Fortunately for this project, geotechnical investigations were performed to characterize the subsurface soils, including borings in 1944, cone penetrometer testing performed in 2002 and 2010, and electrical resistivity tomography surveys performed in 2014. The ERT surveys in the northern and southern locations highlight areas of high resistivity in the foundation soils indicated by warm colors in the ERT graphs. These areas of high resistivity are indicative of sands and gravels. Areas of low resistivity are indicative of clayey and silty soils and are seen in the ERT graphs closer to the ground surface indicated by cool colors. The northern survey shows an area of deep red located in the vicinity of the boils discovered in 2010, which could represent a seepage pathway through the foundation soils. The southern survey also shows the widespread presence of higher resistivity soils, although they appear to be slightly less resistive than the soils in the northern survey. Nevertheless, both surveys indicate the presence of high resistivity, sandy and gravelly soil in the foundation. Cross-sections and profiles derived from CPT logs performed in 2002 and 2010 also aid in the characterization of the foundation soils. Line B prime is a profile of CPT borings along the riverside toe of the levee. Line A prime is a profile just beyond the landside toe. And lines E prime and C prime are cross-sections located near the observed distress in the northern area in 2011 and just north of the location of boils observed in the southern area in the 90s and 2008, respectively. Together, the CPT profiles and cross-sections indicate the presence of a continuous foundation sand layer at Buck Chute Levee. The CPT results corroborate the findings of the ERT surveys and align with the understanding of the depositional environment of the lower Mississippi River Valley, where Buck Chute is located. After the evaluation of the presence of a continuous path of fine to medium uniform sand, an evaluation of the exit conditions for potential seepage pathways is performed to determine if unfiltered seepage exits exist. The field investigations indicate that a landside blanket layer ranging in thickness from 15 to 35 feet is present in the northern area. However, this blanket thins and in some places is non-existent in the southern area. This is due to the presence of a channel deposit associated with Eagle Lake that crosses the levee center line at an angle. The northern area landside foundation soils are within this channel deposit. At the same time, the southern area of the levee is founded on a point bar deposit that is sandwiched between two channel deposits. The cross-sections show that a thick blanket is present on both the riverside and land side of the levee in cross-sections D prime and E prime, but the blanket is absent in the riverside section of C prime, while still being present on the land side of the levee in this section. At first glance, it appears that an unfiltered exit is present in the southern area where the point bar deposit daylights at the ground surface. This is supported by the past observations of boils in this area during flood events. However, the presence of large sand boils in the northern area indicate, although a thick blanket layer exists, there are defects or other openings in the blanket, possibly due to tree root balls or animal burrows, that allow seepage to reach the ground surface. Based on investigations and observed poor performance during past high water events, it can be concluded that an unfiltered exit likely exists in both the northern and southern areas. The next node in our evaluation is initiation. The presence of very large boils in the northern area shows that a significant amount of material is being moved when the foundation becomes exposed to a high river load. Blanket theory calculations were performed to evaluate the potential for BEP in the northern area, and they indicate that the factor of safety against uplift is well less than 1. The combination of past poor performance and geotechnical analysis indicate that initiation has likely occurred in this area during past flood events and was likely to occur during the 2011 event. In the southern area, relief wells were required on 2 separate occasions to mitigate boil activity during flood events. The first set of wells consisted of 6 6-inch relief wells that were installed in 1997. During the flood event in 2005, the presence of pin boils made it evident that the first round of wells weren't sufficient to relieve foundation pressures, and a second round of 3 14-inch wells were installed. There haven't been any observed boils in this area since the installation of the second round of wells, indicating that although initiation of BEP may have occurred during previous flood events, the relief wells appear to be effectively reducing foundation seepage pressures at this location. It's important to note at this point that specific conclusions regarding initiation of backward erosion piping during the 2011 event can't be made due to the intervention efforts that were undertaken during the event. As will be discussed in the next case history presentation on Buckchute, it's likely that these intervention actions either obscured or prevented the initiation of backward erosion piping. The mechanical condition for progression evaluates if the proper materials are in place to hold a continuous and stable roof over a developing pipe. Field investigations have shown in the northern area that there is a continuous, cohesive blanket from the seepage entrance point to the seepage exit point, and that the blanket material contains a sufficient amount of fines to make holding a roof a virtual certainty. The southern area is more complicated. The levee embankment likely consists of primarily CL and CH material that will be able to hold a roof. However, the field investigations and geologic profile have shown that the cohesive blanket thins and is non-existent in some parts of the southern area. The boils observed in the southern area in past flood events have been located several hundred feet beyond the landside toe of the levee embankment. If BEP were to initiate at this location, the near-surface foundation soils between the landside levee toe and the exit point would need to be capable of holding a roof. The foundation materials on the land side of the levee consist primarily of silty sand to sandy silt. While it's possible that these materials contain a sufficient amount of fines to hold a roof, they're less likely to hold a roof than the foundation soils in the northern area and present greater uncertainty in the evaluation of this node. Node 5 evaluates the hydraulic condition required for progression of backward erosion piping. Is there sufficient flow in the foundation to advance the pipe to the impounded water? This node is where the evaluation of uniformity coefficient of the foundation soils subjected to backward erosion piping occurs. Based on laboratory testing of the foundation materials, the uniformity coefficient of the foundation sands is 2.4 on average. For this case history, the adjusted Schmertman method to calculate the critical gradient in the northern and southern areas is used. The seepage path length from the riverside toe of the levee to the seepage exit location is approximately 700 feet for both the northern and southern areas. It's important to recall that the exit locations and conditions for these two areas are different. The northern area will likely contain a hole-type exit through a defect in the confining layer, while the southern area likely contains more of an area-type exit due to the daylighting sands in the point bar deposit. Accounting for the different exit locations, the estimated critical gradient for progression of backward erosion piping is 0.051 in the northern area and 0.101 in the southern area. The peak river elevation during the 2011 flood at Buckchute was approximately 112.9 feet, and the seepage exit elevations are approximately 80 feet in the northern area and 84 feet in the southern area. These values result in average horizontal gradients of 0.047 in the northern area and 0.041 in the southern area. Using the RMC backward erosion piping progression toolbox and research performed by Robbins and Sharp in 2016, the probability of BEP progression is about 41% for the northern area and 0% for the southern area. These results serve as an example of the importance of the exit type when evaluating this node. Although the average horizontal gradients between the northern area and southern area are similar, the likelihood of backward erosion piping progression in the two areas is significantly different due to the difference in the seepage exit conditions. The final node that we'll evaluate in this presentation is breach. As we discussed previously, the intervention node is discussed in a separate case history presentation. Breach in the case of backward erosion piping at Buck-Chute Levee would occur via gross enlargement of the pipe, leading to collapse of the embankment and overtopping flow. Due to the size of the contributing drainage areas, major floods on the lower Mississippi River usually last a minimum of 30 days, but can last as long as several months. Additionally, breach of this levee is different than a dam breach that holds back a reservoir because a reservoir contains a limited amount of water. At Buck-Chute Levee, the supply of water from the Mississippi River is virtually limitless, with the driving ahead for the progression of a breach only being lessened when the flows on the river decrease. Due to the long duration of sustained loading and the unlimited supply of water to drive the breach, it can be considered a virtual certainty that a full breach at this location would occur. Now that each node has been evaluated in detail, we can put together more and less likely factors for backward erosion piping at Buck-Chute and put them into a table. Based on the evaluation of the northern area, there are no factors that make backward erosion piping less likely to occur. The depositional environment and geotechnical investigations indicate the presence of a continuous sand layer in the foundation. Boil activity and material movement in 2008 and 2010 suggest that an unfiltered exit exists through defects in the cohesive blanket and that initiation of backward erosion piping likely previously occurred. The cohesive blanket has sufficient fines to hold a roof, and the average foundation gradient approaches and is very near the adjusted Schmertman method's estimated critical gradient for progression due to the presence of a hole-type exit. Finally, breach is likely due to the unlimited supply of water and long duration of floods on the Mississippi River. The evaluation of the southern area resulted in several factors that make BEP more likely, along with several factors that make it less likely. While the depositional environment and geotechnical investigations indicate the presence of a continuous sand layer and an unfiltered exit, the relief wells seem to be effectively reducing foundation seepage pressures to prevent initiation. The levee embankment will likely hold a roof for the developing pipe, but the near-surface silty sand and sandy silts from the landside levee toe to the seepage exit location may not be adequate roof-holding materials. While breach of the embankment is still likely for the same reasons as the northern area, the average gradient in the southern area is less than the estimated critical gradient for progression based on the adjusted Schmertman method. So after an evaluation of both areas at Buck-Chute Levee, it seems likely that a levee failure due to backward erosion piping could have occurred during the 2011 flood in the northern area. In the southern area, the balance of more likely and less likely factors for backward erosion piping indicate that levee failure was much less likely. The second case history presentation for Buck-Chute will discuss the flood fighting and intervention efforts undertaken at the levee to prevent a failure from occurring. This concludes the backward erosion piping case history presentation at Buck-Chute Levee.